Hi, in this video, we're going to take a look at the Bayesian approach to the normal distribution when both the mean and the variance are unknown parameters. Okay, so this will be the first example of a video where I'm working on a probability distribution that will have two parameters, and we cannot factor the distribution to separate the two parameters apart from each other, that this is going to be a multi-parameter problem. Okay, now we're going to work through examples from Jim Albert's Bayesian computations with R. Here is Jim's website, Bayesball, and here is on Amazon where you can purchase the book. Also, students at the University of Central Florida can download the textbook for free through the library. All right, so let's get down to it. All right, so here for this video, we are interested in the case where we believe our data is coming from a normal distribution, and I want to do a Bayesian analysis, but I don't know the mean and I don't know the variance. All right, so let's take a step back for a moment. Take a step back, think about a simpler problem. All right, so if the mean was unknown and the variance was known, that would be an easier problem. If the mean was known and the variance was unknown, that would be an easier problem. And if you want to go into those aspects of those problems, then you can go in full depth into Jim's website. He has some good lecture notes on handling, the one parameter case of the normal distribution. I really considered handling these a little bit more completely in the video, but honestly, I wanted to keep on track with his textbook. My goal is to work through the textbook and the videos, and so I'm going to let you go on to that. If you are super interested in having those aspects explained, let me know, and I'll generate the video. So let's go ahead and look at the simpler case to get a little bit more grounding understanding going. Let's say that the mean is unknown, the variance is known. Okay, well, then we want to learn about the normal mean when we have an assumed value of the variance. If we assign a non-informative uniform prior on the mean, then the posterior distribution of mu is normal with mean, y bar, and variance sigma squared divided by n. This is very, very natural because you saw this over and over and over in your introductory statistics course. Right now, there's a little bit of nuance going on with this, with the non-informative uniform prior. All right, so in this situation, what we're doing is we're making our prior be over the range of all fathomably possible values of mu and letting it go across. So that's going to be a constant value. So so this uniform distribution will include all possible values that the mean could be for my problem. Okay, in that situation, our posterior will in fact be the likelihood function on the data, because the constant will integrate out when we do our rescaling. And so, it's very natural for us to use, the likelihood function off of that. And so then, boom, we get the normal distribution, easy peasy, lemon squeezy. Now, let's say that the mean is known and the variance is not. I actually did a video on this. It was a pretty brief video. And, I believe it was with like sports betting. Yeah, it was with, the deviation of the results in sports betting compared to the odds. Suppose instead that we are interested in the variance when the mean is known and the typical non-informative prior of the form of 1 over sigma squared is assigned to the variance. Now realize that this is the function 1 over x because that sigma square, we need the square because we're talking about the variance. So this is there is no like squaring in this function. We just have a square on there to represent the variance aspect. So that's actually not even a probability distribution. So it just works out mathematically. We choose that as a prior. The math works out that we still get a probability distribution, and and everything works out very nicely. The reason why we like to do this as an uninformative prior is that it has a ton of spread to it, so much spread that it's not a probability distribution, and that sets it up so that our data has a full voice in our posterior. So if I don't want my prior to bias the results I ultimately get, I pick an uninformative prior with a lot of spread, possibly to the point where it's no longer a probability distribution, and then boom, my data is doing all the speaking. Well, that's not necessarily a good idea, right? What if I had very, very good, reliable knowledge about the situation? Then I wouldn't want an uninformative prior. I would want my knowledge to speak and be heard in my posterior, but that's not the case for this example. Another situation where we would not want the prior to be uninformative, let's say that I don't trust my data because I know that there's problems with the process of collecting data, but this is what I've got to work with because, I have to get paid. I need my paycheck. So I could, if I don't trust my data, but it's the data I've got to use, I could use a prior to compensate for the shortcomings. Some good tricks there. All right, so in the situation where the mean is known, the variance is unknown, and we pick the standard uninformative prior, then sigma squared is going to be distributed as S times chi-squared, inverse chi-squared distribution, where S is the sum of the squared deviation about the mean. All right, and so then we have the distribution going on, and it's directly connected to the inverse chi-squared distribution. We actually generalize this to a gamma, inverse gamma. Like if you go into Wikipedia's conjugate prior page, it will talk about that. But Jim puts an emphasis on inverse chi-squared instead, which is easier for us to work through mathematically. All right. So with a non-formative prior, we have our observations from a distribution, a normal distribution with mean mu and variance sigma squared. And we do not know what the mean is. We do not know what the variance is of our data, but we know what our data is. So we assume that we have little prior knowledge about the location of either the mean or the variance. And so we assign the usual non-formative prior. Here is at 1 over sigma squared. Okay, and notice that this has nothing to do with the mean, right? And this is going to be back to that uniform mean aspect. Well, the uniform mean, any uniform distribution has to have a maximum and minimum. Those maximums and minimums are going to be the maximum possible value for mu, the minimum possible value for mu. And all the math will work out for us. In the general case where both parameters are unknown, the likelihood function is given by this. Okay, so if you want to derive this, what you're going to do, you're going to take the normal distribution, take the product of the normal distribution for every single time that you plug in a value, and then I'm going to be doing a product that involves E. That E is going to lead to a sum in the exponent. I'm going to have a bunch of square root 2 pi's and sigma squares, and sigmas all being multiplied together. And then I'll have this term also in there. If I go through, do the pencil and paper mathematics, then what I'm going to have is going to be proportional to this output here. Now, when we do Bayesian statistics, we always want probability distribution on the parameters of interest. The parameters of interest are mu and sigma squared. Everything that does not have a mu and does not have a sigma squared that is multiplying the rest of this is just a constant value for the purpose of this problem, and that's just kind of get in the way of our computations. So what we're going to do is we want probability distribution. So we're going to rescale our function so that I'm going to multiply by a constant that whatever constant it would take that ultimately I have a probability distribution when I'm all done. All right, and so what we're going to do, we're going to use our mathematical statistics 1 course information. We're going to take this as a kernel, and I recognize that as being connected to the normal distribution. I'll get the scalar. Boom, I know that this is normal distribution. I've got the results I need. And so ultimately, I'm going to have this as my posterior when we put everything together. So here's the likelihood function multiplied by the prior. Boom, I get my posterior. And so this up to, except for multiplying by a constant, is a probability distribution that I recognize as being the normal distribution. And so then I can go further and start working through some more details on this. So let's subtract and add the sample mean from within the sum of squares term. If I go through and I slug through the mathematics, I can see that this exponent here, this portion of the exponent, is equal to this. Okay, well, this part right here, I don't see a mu, I don't see a sigma squared, right? So I might be able to simplify this. Let's see if we can. All right, well, okay, so there's a sigma squared here that's going to get in the way of simplifying, but we can still make things a little bit easier. And so I'm going to use this identity, and I'm going to rearrange my terms, and my posterior distribution is going to be proportional to this right here, like that. And so we have the joint posterior density in product terms. Okay. And now, when I look at this, I notice that this part here does not have a mu. And this part here has a mu and a sigma squared. So how we typically approach this problem is that we look at the sigma part first. And if sigma was nailed down and figured out, then this part, if sigma was like isolated, then I've got the mu part left over. Okay, I spoke backwards. This does not have a mu, and this one has a mu. I got it backwards. I apologize. So how we operationally work with this is that we use this part to nail down the sigma from a theory point of view. And then once that's nailed down, then I use this part to approach the mu. Okay? And now the whole distribution, I cannot break this apart because there's no way for me to break the mu and the sigma squared in a probability distribution sense to break this up. So I'm stuck with these together. I have to do like a multivariate analysis. This is harder than the single parameter problems. Okay, so how we're going to think about this is that I've got G of the variance given my data, so variance given data, and then I have mu given the variance and my data. And you see how I've got that set up, that this part corresponds to the variance portion, and this part corresponds to the mean given the variance and the data. The first term of the product represents the posterior density of the mean conditional on the variance. Okay, so we recognize this as a normal density with mean y bar and variance sigma squared over n. Boom, look at that. That's, check this out. This is easy peasy lemon squeezy. If I do a little bit just dividing by a fraction manipulation, I can recognize this as mu having normal distribution with mean y bar and variance sigma squared divided by n. All right, now the second term is proportional to a marginal posterior density of sigma squared. And if we look at this for a moment, we recognize that marginal density as the scale times inverse chi-squared form of this. So I have the sum of squares deviation times an inverse chi-squared distribution for this part. Boom, check that out. Where the degrees of freedom are n minus 1 and the sum of squares is this. All right, so the posterior density is commonly called the normal inverse chi-squared distribution. In this setting, one typically is interested in inferences about the normal mean, and we base this inference on the marginal posterior density. So most of the time when we're in this position, I don't know mu, I don't know sigma squared, but honestly, the one I care about is mu. Sigma squared, I don't know it, so I can't take it for granted. I have to go through this, multivariate approach to my Bayesian analysis, but it's not the focus. It's not the center of this. So this is obtained by integrating out the sigma squared from the joint density. Okay, so we can use our earlier expressions and write the integral as this. So I'm taking the previous expression and I'm manipulating it in the right way. And then I'm going to do integration to get the sigma squared out of there. Now we can simplify this integral by invoking, a well-established identity with the gamma function, or you could say the gamma distribution. They're the same thing, really. And so with this, if I want to use this formula to make the integration simpler, because I recognize it and I know it, I set A equal to n over 2. I set B equal to S, that sum of squares difference from the mean, plus n times y bar minus mu squared. And so if I do that, we're going to see that we're going to get a marginal posterior density of mu given by this curve right here, which I can rewrite, which in this format, I can see that this is functionally a t distribution. So after some manipulation, we can show that this is a standard random variable where little s is equal to the square root of big S divided by n minus 1. And so the sample standard deviation is little s. And so we're using a standardized t distribution with n minus 1 degrees of freedom. So something about this should be ringing in your head. It's like, wow, this looks a lot like the results I saw in introductory statistics of the t distribution, approximating the normal distribution. It's coming full circle on us right here, right now. And so this is a very familiar result from sampling theory. If one samples from a normal population and we don't know the variance, then we get our well-known t statistic. Now, ultimately, why is it in introductory statistics we use the t statistic instead of normal? Because not knowing the variance, by estimating the variance, we're actually inducing more variability, more spread, more dispersion in the system. And so here, we're dealing with a t distribution with n minus degrees of freedom. Our results switches the role of the data and the parameter of mu. By assuming the non-informative prior on mu and sigma squared, the standardized marginal posterior of mu with fixed data has the same t distribution that we would get in the classic frequentist approach. I mean, that to me, that verifies the Bayesian approach works. If we're taking this way of handling a problem, because it ultimately shows that the Bayesian approach is a generalization of the tools that are already established in the frequentist toolbox. All right, so let's talk about the Bayesian frequentist correspondence. What is the implication of the similarity of frequentist and Bayesian distribution results? It means that classical and Bayesian inferential procedures are agreeing in this setting. For example, suppose one is interested in a 95 interval estimate of the mean mu. Then the standard frequentist form has the standard confidence interval that we've grown to love, where t is the upper 0.025 quantile of the t distribution with n-1 degrees of freedom. In repeated sampling from the normal distribution, this interval will have a 95% frequentist coverage. This is equivalent to saying that the probability that my data is going to satisfy this equation, this inequality, is equal to 95%, where the probabilities could be manifested by repeatedly taking observations. Now, from a Bayesian viewpoint, we could say that we've got y bar minus t times s divided by square root of n, and here y bar plus t times s divided by square root of n, and mu in the middle. Now, it looks very, very similar, and we're getting a very similar result, but remember, this is a different point of view. Here, we're treating mu as an unknown with its own likelihood distribution. And we're treating the data as hard fixed values in constants because we've already collected the data, we've seen them, it's not varying, it's not changing. This means that the posterior probability that mu is contained in this fixed interval is a 95% chance. The actual computed intervals of the standard frequentist and Bayesian procedures are identical, but the interpretations are very, very different. The frequentist statement refers to the characteristics of the interval in repeated sampling, and the Bayesian statement refers to the property of this interval conditional on a particular set of observations. A similar correspondence is true for inferences about the normal variance. We earlier noted that the marginal posterior density for the variance is of the form sigma squared is distributed s times inverse chi squared. Equivalent, one can say that the posteriors of the function s over sigma squared is chi squared with n-1 degrees of freedom. And this is something that your professor probably talked about quite a bit when you start talking about chi squared. From a frequentist perspective, if sigma squared is fixed, then this statistic of the sum of squares difference from the sample mean over sigma squared has a chi-squared sampling distribution. Again, this corresponds means that the Bayesian inferential statements about a variance, assuming a non-formative prior, will be numerically equivalent to the corresponding frequentist interval statements. But the interpretation of these statements will be different. For an interval estimate, the posterior probability that a particular interval contains sigma squared is the given level. In contrast, the confidence of the frequentist interval refers to the probability of containing the parameter in repeated sampling. And so the frequentist approach talks about a sampling point of view, and the Bayesian point of view talks about the probability that the parameter is within the interval that we believe after we've collected our data. All right, so now let's talk about using an informative prior. The form of the posterior distribution of mu sigma squared in the non-formative case suggests that the form of an informative conjugate prior. We assume that the prior for the mean conditional on the variance has a normal distribution with mu zero and a variance of sigma squared divided by n sub zero. Then we assume the marginal prior on sigma squared is distributed by an S naught times an inverse chi squared. Okay, so we've got a whole bunch of hyperparameters floating around. We've got mu naught, n naught, S naught, nu naught, all just came into bearing on this. All right, so the prior mean is mu naught. This is our, like our best guess of the mean of the mean of the mean that we're trying to get. N naught is a number of prior observations. And so this reflects how confident I am in the results. That remember that if I'm very, 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 very confident in my prior, I'm going to have it have very little variance. If I have very little confidence in my prior, then I'm going to give it more variance so that the data doesn't get biased. All right, and so this is like a fictional sample size that reflects how confident I am in my prior. Now we have a prior guess of the variance. And nu naught represents the precision of the guess expressed again in prior observations. If we apply this prior density, then it can be shown that the posterior density has a normal inverse chi-squared form. Okay. First, if we condition on sigma squared and combine the normal prior on mu with the normal likelihood, then the posterior density of mu is going to be given by this. Boom. Okay, so check this out. All right, so I have nu naught is so I'm going to take an informative prior. I'm going to choose normal distribution because that's going to work out well for my problem. I actually believe that that's the correct call, and that has some nice mathematical properties from it being a conjugate prior. All right, so mu sub 0 is my prior's mean. Y bar is my data's mean. N naught is like a fictional sample size reflecting my confidence in my prior, and N is the number of observed data. And you'll see that this mu sub 1, is actually a weighted average where the weights correspond to the sample sizes. So N naught is my fictional prior sample size, and N is my actual observed sample size. And N1 is going to be the sum of the two. We can also show that the variance is going to be S1 times inverse chi-squared, nu naught, where the nu1 is nu naught plus N. And then S1 is a little bit trickier, but I've got the two variance aspects, and then I'm adding on a new dispersion aspect. Okay, so why do we like this? Because with these formulas, I actually don't have to do any like multiplication. I don't have to do any rescaling. I actually just have to go, hey, what's the mean variance sample size of my prior? What is the mean deviation and sample size of my data? And I can put them together immediately and get a prior without having to go through a whole bunch of, like nuanced computations. I don't have to do anything with the Monte Carlo Markov chain. I don't have any, figuring out the density and figuring out what the area under the curve is and rescaling to get the probability distribution right. None of that. I just go, I use these formulas, boom, I've got it, easy peasy lemon squeezy. If you are following me up to this point, what's on the screen of formulas will be super easy for you. Okay, so now let's talk about normal data with both parameters unknown. Okay, so that's what we've been talking so far, but the previous stuff was from notes on Jim's website. Now I'm going back to the textbook. Let's illustrate Bayesian computations for this problem. Suppose that we're interested in learning about the distribution of completion times for men between ages 20 and 29 while running the New York Marathon. We observe the times of 20 runners in minutes, and we're going to assume that they represent a random sample from a normal distribution, mean mu and standard deviation sigma. and we're going to go ahead and assume the standard non-informative prior. All right, then boom, I know that this is going to be my posterior density, where n is the sample size, y bar is the sample mean, and S is the sum of the square difference of y from y bar. This joint posterior has the familiar normal inverse chi-squared form. The posterior of mu is conditional on sigma squared. And so conditionally on sigma squared, so when sigma squared has been nailed down, integrated out, figured out, then mu is going to be normal y bar sigma squared divided by n. And I'm inconsistent on variance or standard deviation in my notes today. Please forgive me. Now, the marginal posterior of sigma squared is going to be S times inverse chi-squared. This should be a times, not a subscript, where the chi-squared denotes an inverse chi-squared distribution with new degrees of freedom. All right, so let's go ahead and actually, construct this, because I've been doing a lot of mathy talking. Let's go ahead and take the marathon times data set from the LearnBase package. Here is the data that I've got. So this is their marathon times in minutes. What's the average? Okay, so we can see that it takes over 4 hours for most people to complete their marathon, or for this sample to complete their marathon. What's the variance of this? Okay, so 2450, about that. And let's go ahead and look at the histogram of times. All right, so 150, I promise you I will never run a marathon that fast. I also promise you I'll never run that slow on a 400. I'm coming in under 4 hours, but not by much. So we know where I land, and we can kind of see what the shape is. We only have 20 observations. We don't have a whole lot of data. And so remember, whenever I'm in a small data problem, it's a good time to invoke Bayesian statistics, because I can use the prior and to fill in the gap of lacking data to get a more complete, more reliable analysis. All right, so let's go ahead and take our marathon data, and then we're going to take the mean and the variance and do a contour plot on our posterior. Okay, so with a contour plot, and this is actually the log of the density, that's why we have negative numbers on there. We see that this point here is the most likely. We think of this as like a contour plot from Calc 3, or from like reading a map, a topographic map, if you were a Boy Scout or in the Army or Marines or something like that. Here is where this is the mode of the distribution where it's most likely. And so if we view this as this is the peak of a hill, this is every point on this elliptical circular line all have the same height on the hill. These all have the same height, the same probability values, and these all have the same height on here. All right, now the lines here are very close. That means that if we interpret this like a hill, it's very, very steep. We have a very rapid change in the probabilities as we go south from here to there. Well, if I go from here to there, it's a very gradual decline. All right, so let's go ahead and summarize the posterior distribution by simulation. So we can simulate a value of mu sigma squared from the joint posterior by first simulating sigma squared from S times inverse chi-squared distribution, and then simulating mu from the normal, given that I've nailed down what the variance is. All right, so let's go ahead and do exactly that. All right, so I've got the marathon times, the mean, taking the square of the difference, then adding them all up, that's my S. N is the number of observations I have. Now here, I'm going to take that S, divide by a random chi-squared value with the corresponding distribution that we've established. And then from here, I'm going to take the mean there. I'm going to take the sigma squared here. Realize that this is a vector of 1,000, of length 1,000. And so each entry on this vector represents an estimate of the standard deviation, or a random value of the standard deviation from our distribution. So here we are randomly generating a standard deviation value. Then we're using that standard deviation value as a fixed value, and then using that to generate the mean off of it. Okay, and so now I'm generating random values that correspond to that curve that we were just looking at. Let's go ahead and overlay those points on there. All right, so now you'll notice that at the peak that I was talking about, that's where we see the densest part of the dots. That's where the most of them are. And we can see the density of the dots decrease as the contours go downhill. All right. So now we can use inferences about the parameters or functions of the parameters, in multiple ways. So if I have a problem that's rather difficult to get to, I can actually go and do a simulation like this and work out any bizarre, crazy thing that I wouldn't be able to do by pencil and paper mathematics. So let's go ahead and construct a 95% interval estimate of the mean. Well, I'm going to take the mean value of the dots, that's the x coordinate here, and I'm just going to do a 95% interval on here. Boom, look at that. So I believe, between 255 and 300 is my 95% interval. It's called a credible interval, by the way. And we can also do the same thing with the standard deviation. And so with the standard deviation, I play the same game. Now, when I grab this, remember that this is scaled at variance. I take the square root. Then when I do the quantile, boom, you can see that my 95% credible interval is from 37 to 72. Okay, and so now I've got an interval estimate, which tells me a level of precision of my understanding of the mean and the standard deviation. All right. Gone over a lot of stuff, a lot of heavy lifting math, good, good stuff. I hope you've enjoyed this video. I hope this video has helped you. And I'm saying goodbye. Remember, life is short. Do math.